Welcome, everyone. Let's get started. Course announcements. So just to clarify, it is absolutely fine to take as a given that the problem of determining whether or not a Hamiltonian cycle exists is NP-complete. We stated that in class. It's totally fine to take that as given. You don't have to prove it. Are there questions? Okay, let's get started. So I wanted to start out with a fun side note. So this came up in office hours today, and I thought it was really nice, so wanted to discuss it. So it concerns 2-sat. So remember we said that Boolean formulas could be written in the form of 3-sat. So we could rearrange things, possibly add variables, move around clauses, so that we ended up having 3 variables in each one of the clauses. Now, this is not possible to do with 2 variables. You could do it with 4 variables, but there's something special about 2 variables. You can't go down to 2 variables. 2-sat is like 3-sat, except that the clauses in the formulae have 2 variables, not 3. So here are one clause, another clause, another clause. Just 2 variables. Is 2-sat NP-complete? What can we say about 2-sat? It is in NP. Yeah, so sorry, I realized I didn't define what exactly like 2-sat is. 2-sat is just the problem of working out whether a two conjunctive normal form formula is satisfiable. So it's exactly the same as 3-sat, except if you're given a formula, it has 2 variables in each clause, not 3. So is this formula satisfiable? More generally, is a formula with 2 variables in each clause satisfiable? So it is definitely an NP because you can just find, if you found a solution, you could use that as your certificate. So all we would have to show it's NP complete is to show that it's NP hard. Something else reduces to it. A couple of people saying that no, it is not NP complete. Good point, though, in the chat. If it's NP complete, there would be a 4/3 approximation algorithm by the same approach that we did before. We had an 8/7 approximation for 3-sat, max 3-sat, I guess I should say. There would be a 4/3 approximation for max 2-sat. So yeah. So turns out that 2-sat is actually polytime solvable. And this is basically why it's polytime solvable. suppose you picked a clause. Maybe it's the first one. You can suppose without loss of generality that it is x1 or x2. The reason you can do that is you can just renumber the variables so that the first two that you're looking at are 1 and 2. Just renumbering them doesn't matter. You can also flip the variables. So here we started out with x1 and negative x2, but we could just flip all the x2s, and that's not going to change whether it's satisfiable or not. So now this is, flip all the negatives to positive and all the positives to negative. So now it's first clause is x1 union x2. Case 1, x1 is true. And you have either x1 being true or x2 being true. What can we do? We can eliminate all the clauses with x1 in them, since we know that those are true immediately. And if we have any clauses where there is negative x1, then we can immediately remove it, because we know that that's false. So let's think about this now. We've taken out a bunch of clauses. We have immediately some other variables that we know are true, because if we set, for example, if we said, OK, x1 is equal to true, that means negative x1 is equal to false. That means that if this clause is going to be true, we have to have x4 be true. OK, so that immediately gives us some other variables that are true or false, like x4 above, since every clause has two variables. This is the important thing. Because we're in 2SAT, when you set one variable in a clause, you immediately know the identity of the other variable in the clause. OK, so now what do we do? Well, we can repeat these steps here with the other variables that we just set, just like we did for x1. We can cascade, basically. So once we know x1, we know x4. Once we know x4, we know anything that's in clauses with negative x4, and so on. We can keep on going down the line. Once we have one variable, we immediately can we can throw out a bunch of clauses that contain the variable in its true form, and we have a bunch of clauses with the variable in its false form, where we can eliminate that variable, and we know that the other variable is true. So what happens? Well, eventually we're left with either the entire formula being satisfied, or there are a few remaining clauses. Or I guess I should say there's also a possibility that we end up with a contradiction, where we had one clause where x4 had to be true, and another clause where x4 had to be false. Assuming we don't end up with a contradiction, we're eventually left with either the entire formula being satisfied, or a few remaining clauses where we haven't changed any of the variables. We haven't set any of the variables. If we're in case 1, we're done. If they're in case 2, we've just reduced the number of clauses we have to consider. And we've said that if we can solve the problem, then we can solve, if we can solve those clauses, then we can solve the entire problem. So in that case, we can just recurse down to those few clauses. In case 2, remember we had two cases. x1 is true. Case 2, we had x2 being true. That's just the same thing. It's OK if you didn't get all the details here, but this is just a general intuition for a pretty remarkable fact that 2SAT is not the same as 3SAT, that it is way easier. It's polynomial time. And again, here's just the overview. Once we set one of the variables in 2SAT, we immediately know the identity of a bunch of other variables. And we can immediately set all of those. And once we've set those, we can set a bunch more. And this cascades down. And we either set all the variables, run into a contradiction, or we end up with a bunch of clauses that are independent of the variables that we set, and we can just focus on those. And we can keep on doing this. Are there questions about this? I only brought this up because it was brought up during office hours, and I thought it was cool. So this is independent of anything else we're talking about. Where does this break down for 3 sets? So that is the important question here. The reason why this breaks down for 3 set is because once we set one of the variables, we don't immediately know which one of the other variables in the clause. There are 2 more variables in each clause. So we don't immediately know which one of those is true. There is none of this cascading. This is the step that fails. We're not left with entire clauses. We're left with partial clauses where we've changed the formula. And we have to then do a bunch of casework, and that casework becomes exponential. We say, well, either this second variable is true or the third variable is true because I've set the first variable. But then you have this exploding casework. You have exponential branching. I'll leave you to think about this thing. Again, this is just something fun to think about. Does this bound also hold for max 2 sat? I don't know. Go look it up. I don't know about max 2 sat offhand. Last time, yeah. So there's a question about actually, just one moment, sorry. I'll be back in one moment. Sorry about that. That was me doing the stupid thing of forgetting to plug in my computer. There's a question about the approximation algorithm from last time. Consider the clauses independently. This is a question about last lecture. Why do we consider the clauses independently while computing the expectations for each of them? Because fixing one variable of a clause can fix variables of other clauses. So the reason why we could do this last time is because of linearity of expectation not requiring things to be independent. The reason why we could do all that analysis last time is just because when you are computing the sum of 2 expectations, even if the 2 things that you're looking at are dependent upon each other, it is possible to compute their sum via linearity of expectation. I'm happy to answer more questions on that via Slack, but that is a question from last class. So. OK, let's go on. Let's actually start talking about neural nets now. So we're going to now look at, or at least for today, we're going to look at classification problems. So classification problems in general involve taking some input data and inferring a class label from some sort of finite set. So for example, we could be doing 2-label binary classification. So m equals 2. That's just what it means to have 2 possible labels. The number of possible labels in your label set is just 2 here. And here, the 2 labels are green and blue. You can imagine that you need to classify these 2 classes of data points. So binary classification comes up in answering yes/no questions like, does this image show a tumor or not? Is it safe for my self-driving car to drive in this particular way? There are obviously a lot of binary classification tasks. There are also more general classification tasks where you have many different possible labels, like you labeling images, dog or cat or book, and so on. So there is a typical paradigm. I'm not really since this is not a machine learning class, I'm not really going to go into the full paradigms of different kinds of machine learning. But there is the paradigm of supervised learning where you are essentially given labels for a number of data points, where you see some examples, x1 through xn, where each one of those is a vector. I'm using this superscript notation. So it's basically just because there isn't room for enough subscripts, because we might want to index into these vectors. So x2 is not x squared here. I realize it's really confusing, but this is common notation. x2 just means the second one of the x's. Since each one of them is a vector, yeah. OK, so we're given these data points, and we're also given labels which correspond to those data points. So each yk is the label associated to xk. And there's sort of an implicit assumption that there is some function in the real world that is labeling our data points correctly. So like there is some function in the real world which is taking an image and saying, is this a cat or not? Now, that function could be people having labeled these images by hand, but we're sort of assuming that the data has structure. There's a comment that you can use parentheses around these things. Yes, some people would use parentheses around these things. That's another notation. I might use that as well. But yeah, since each of these is a vector, we're never going to be taking, it doesn't make sense to take exponents of a vector. And so that's why it's sort of possible to write that down. Because it's like, it's not you couldn't take x squared because x is a vector. OK. Now, we're observing these data points and these labels. And what we basically need to do is we need to come up with a function to predict some new labels. Whoops, sorry. We want our function to be good at predicting the labels on the data points that we've already seen. And we would like it to be, to say, OK, well, my function is anything inside this circle is colored blue, anything outside is colored green, or anything on this side of the line is colored green, and anything on this side of the line is colored blue. So we would like to infer from the data that we've seen a classification into the different possible labels. OK. Now we're going to be looking at perceptrons today. So in some binary classification tasks, the data are going to be linearly separable, i.e. the labels will be from a set of just two elements, and the labels, you can just write them as +1 or -1. So that you can think of this as satisfying y of x is just, backing up. If you're in a binary classification task, there are just two labels. So here we're looking at a situation where the labels are just +1 and -1, just for convenience. If the data is linearly separable, that just means that if you're on one side of this line, w.x, you are in one class. And if you're on the other side of the line, you are in the other class. The sign function is just saying you're +1 if positive and -1 if negative. Again, this is just because it is the equation of a line. Anything, if you have the equation of a line, which the equation of a line, I guess I should say, the equation of a line through the origin is going to look like this in this summation, or you can write it as w.x. And so if you're on one side of the line, w.x is greater than 0. And if you're on the other side of a line, w.x is less than 0. And so you can express a linear classification where the line goes through the origin as sine of w.x. w.x is either positive if you're on one side of the line or negative if you're on the other side of the line. Now, Why is this the case? Remember, we saw before that hyperplanes in general, and in particular lines, have the equation w dot x equals 0. And so you can think of the equation of the line as being w dot x equals 0. And if you move off the line, you move off the line either in the direction of w dot x being positive or w dot x being negative. There's a question. Only through the origin because we are missing the constant. Yes, this does not represent affine subspaces. It does not represent lines or hyperplanes that are moved away from the origin. More questions about this? Why this is true? Again, this is just a two-dimensional version of it, but you might have linearly separable points that live in some higher dimension. We're thinking of a general dimension D. So in general, we have a hyperplane which separates the points that are on one side from the points that are on the other side. More questions? In most situations, we will not have linearly separable points, but in some situations we will. Okay. So what we now need to do is we need to learn a function, w dot x, from observed data, some data points with their labels. And again, the labels, since it's a binary classification task, they're just two possibilities, and we're going to assume that they're +1 and -1 just to make it easy so we can write down sine of w dot x. Cool. If we have learned the classification function w dot x, then that enables us to predict the class of a new data point. We can just say which side of the line is it on by computing w dot x for some new data point x. Okay, so how are we going to actually do this? Our goal is to learn a weight vector such that this equation holds, such that the labels are correctly assigned for every one of our input data points, k equals 1 through n. Let's see how we can do that. So our algorithm will be to start with some candidate weight vector until we find w0, and construct some more weight vectors until we find a w that works. Suppose we have wj. Then we're going to suppose that we aren't done. Suppose that this weight vector doesn't work. That means that we can find some point out of our data which is incorrectly classified. It means that there's some k such that yk is not equal to the sign of this current weight vector dotted with the data point. And now we're going to create a new vector, a new weight vector, which is equal to wj plus yj, which remember is +1 or -1 times xj. This is not intuitive yet. I will go through the intuition for why this is the case in a bit. But what we are doing basically is we're taking our original weight vector and we're saying, okay, we're going to either add or subtract one of our data points to this weight vector. So we can keep on doing this until our new weight vector linearly separates the data, which is what we're trying to do. We don't know that we will end up with a weight vector that linearly separates the data. We need to prove that. So what we have is, again, an iterative algorithm. We start out with some weight vector W0. I realize I should have written, I think I'll write it on the next slide. We're going to start out actually with the initial weight vector being 0. And then we're going to construct some more, we're going to construct some some weight vectors, W1, W2, and so on, until we end up with a weight vector that actually linearly separates our data. And the iteration scheme will be to just take the weight vector that we have, find something that it misclassifies, and either add or subtract the corresponding data point. Let's see how this works. Yeah, again, I am sorry for the discrepancy between these two slides. I meant to say we're going to start out with zeros, actually. And just, let's say we start out with W1 equal to zeros, and we're going to just construct W2, W3, and so on. Again, I'll fix that in the slides. Apologies. Is there a question now? Or did that fix it? Oh, yeah, sorry about that. Did I? Oh, yeah, there was a typo here. I'm really sorry. This should be YK, XK. I only fixed that typo on this slide. I'm really sorry. Again, let's walk through this algorithm. We start out with a weight vector of all zeros. We find some point that is misclassified. At the start, we can just pick any point because everything is misclassified, presumably, by a weight vector of all zeros. And we pick, we then update our weight vector according to the following thing. We take the weight vector we were at before, and we add either, we add yk, which again is a constant, it's +1 or -1, times xk, which is our data point. So we're going to need two assumptions to prove that this algorithm works. The first one we're going to need is that the data is indeed linearly separable. We're going to have to assume that there is some hyperplane that separates the data into the +1s and the -1s. And so how can we frame this assumption? So let's assume that there is a unit weight vector which defines our hyperplane. There is, for every hyperplane, there is a unit weight vector that defines that hyperplane. And let's assume that none of the data points actually lie on the hyperplane, so there is some margin. There's a margin greater than 0, so that for every one of the data points, those that lie on the positive side, or at least gamma, are margin away from the hyperplane. That's for the positive data points, so the ones which have +1 as their label. And let's assume that everything on the negative side, so with everything with -1 as its label, is at least negative gamma away from the hyperplane. So this is saying not just that you are linearly separable, but there is some like distance that you are away from the hyperplane separating the positives and minuses. That makes sense if you have things which are linearly separable, but there's like exactly one weight vector which separates them. There's no leeway, as it were. Then it should be harder to solve. So we can summarize this as if you were to, if you want to summarize this and this in a single equation, you can write that yk times this expression is greater than gamma. Because if yk is +1, so if you have positively labeled points, then we want this to be bigger than gamma. And if you have negatively labeled points, then we want it to be less than negative gamma. And so you can just write this as yk times w star dot xk is greater than gamma. Are there questions about this? Again, this first assumption is just saying that we are assuming that we have some data coming in. The data are labeled xk. They are vectors. The vectors lie on one side or another of a hyperplane. If they lie on one side, then they are at least gamma away from it, and they have the label +1. If they lie on the other side, they're at least gamma away from it on the negative side, and they have the label -1. How does this guarantee that the weight vector will converge? We are nowhere close to proving that yet. That is a really good question. This is not, these are assumptions that will make our proof work. We are about to go through the process of proving it. We're going to need one more assumption. So I'm going into this, by the way, if you're thinking, well, data is never really linearly separable. I'm just going into this because I think it's really instructive to see that it is possible to prove how to classify linearly separable data using a perceptron, but at the same time that it is it's like actually not that quick. And we will be looking at much more complicated data in the next couple of classes where we need more complicated learning rules, which don't necessarily come with provable guarantees. Okay. So great. Now the second assumption that we're going to need is that the data is bounded. I'm just going to assume that xk for every one of the k's is less than or equal to r for some r. We don't have infinitely growing data. Okay, so they're just natural assumptions. So the first thing we're going to do is we're going to prove that if you're at the j plus first weight vector, remember we're iterating on these weight vectors. We say we start out with zeros, and then we just we keep on making better weight vectors until eventually we end up with a weight vector that actually works at linearly classifying the data. So we're going to claim that at the j plus first step, we are at the size of the weight vector is at least j times gamma. It will be clear why this is useful. So W star, which is our sort of special weight vector. It's the weight vector that we would like to find. If we dot W star with Wj plus 1, we can just rewrite this as W star dot Wj plus Yk plus Yk times Xk. That's just our update rule. That's how we wrote it as Wj plus 1 as a function of Wj. And this is with Xk being something that was misclassified by Wj. So we can just break down this dot product. And I'm pulling out Wk here because Wk is just a constant. It's +1 or -1, depending on whether it's a positively labeled point or a negatively labeled point. Oops. I'm sorry. One moment, I have an issue in my slides. I'm very sorry about that. I'm honestly surprised it hasn't happened before in the class. The reason why it happened, for what it's worth, while I'm just getting set up again, is that it's really the animations in Beamer, which is the LaTeX package I'm using to make these slides. They are very finicky, so it's very easy to accidentally make things disappear, which is what I did here. So I'm really sorry about that. Let's go back here. I think this should work now. There. Okay. So going back here, we broke down our dot product into these two things. And what we can do is we can say, okay, well, we actually know what this thing is. This thing is at least gamma. And so let's just write this. This thing is greater than the first term plus gamma. And now what can we do? What should be our next step here? What happens if you see something like this in terms of wj plus 1 is greater than w star dot wj, which is the same thing as over here, just one index lower plus gamma? What would be a good next step to do? So there are a lot of good suggestions here. I'm going to go with the induction route, but I think that the other suggestions would also be very reasonable ways to move this stuff around. So just if you see something like this is the j plus first thing, this is the jth thing, and we see that when we go from the jth thing to the j plus first thing, we add gamma. So we could just do this recursively. We could say, let's write this in terms of j minus 1. And that's going to be plus 2 gamma. And then keep on doing this. And we end up with this. W star dot wj plus 1 is greater than w star dot w1 plus j times gamma. We've just done this j times. And then we like that because w star dot w1 is just 0 because we start out with 0. So backing up, what we have is that w star dot wj plus 1 is growing by at least gamma each time. And so eventually it's going to be at least j gamma. That's not what we needed to prove here, though. That's not what we needed to prove. We needed to prove that the 2 norm of wj plus 1 is at least j gamma. And that's not quite the same. How do we get from here to here? So there's a question, if wj plus 1 is w star, then we would end up getting the norm of wj plus 1. Yes, we would. It would actually be squared. If these two things were equal, we would get the squared norm. Also, we don't know that we've converged yet. We don't know that we have gotten to W star. We are trying to show that eventually we will get to W star, but certainly, for a random J, we have not gotten there. How can we relate these two things? We have the dot product of two vectors, and we have the norm of one of those vectors. I think people are overthinking it. Yeah, so we have the dot product of two vectors, and W star, remember, is a unit vector. We could assume that the ideal vector that we were looking for is normalized so that it's a unit vector. That's all we need. We have that J gamma is less than this dot product, but the dot product of two vectors is less than or equal to the norm of one times the norm of the other. And since the norm of this first one, W star, is just 1, then this is just equal to the norm of Wj plus 1. And that proves the claim. Which doesn't finish the proof. It proves this super enigmatic claim, which I just pulled out of a hat and said would be useful. I'm not telling this should make you still really dissatisfied or confused. Probably a mixture of dissatisfied and confused. Now, let's finish the proof with another claim. And this will be another mysterious claim, but then it will be useful. So let's prove that Wj plus 1 norm squared is less than or equal to Jr squared. So what we previously proved was that the norm was greater than J gamma. And now we're going to prove that the norm squared is less than or equal to J R squared. So how can we do that? So let's just write out again what we know. If we have one of these, I wouldn't know what to do with this thing, except to write out what I know is true about Wj plus 1. So I know that Wj plus 1 is equal to Wj plus Yk xk, where xk was something that was misclassified. That was my update rule. So if we only know our update rule, we have to plug in our update rule. Now, the 2 norm of a vector squared, whenever you see norm of a vector squared, you should think in terms of writing it as the vector dotted with itself, because that's just another way to think about the squared norm. And when we have the vector dotted with itself, we can expand that. So this is this thing expanded. Ugh. How does that help us? Well, let's look at these 3 things by themselves. This one. Why is it less than 0? Less than or equal to 0? What this is, again, is Wj, our jth iteration, dotted with this example xk that we found was misclassified under Wj. Yeah, so since xk was a misclassified point, what does that mean? It means that Wj.xk was not equal to the correct label. It means that we had the wrong one. So that means there are only 2 possibilities for yk, +1 and -1. If this is not equal to this, then it means that they are of opposite signs. So that means either this thing is positive and yk is -1, or this thing is negative and yk is +1. Either way, if we multiply them together, we get something that's negative, because something negative multiplied by something positive is always negative. Questions about that? Again, what we're saying is that there was this misclassified point, which this is the reason why we did this particular update rule. It's because when we have this cross term in the computation here, we want this cross term to be less than or equal to 0, and we can ensure that it's less than or equal to 0 by picking an update that is given by yk xk. Okay, so now what can we do here? Well, we can simplify this. We can just say that this, sorry, I guess this should be an equal to, because this is just literally plus or minus 1. And then by assumption, we know that every one of our data points has squared 2 norm less than or equal to r. We're almost there. This squared norm is less than or equal to the jth, this is at j plus 1. It's less than or equal to the thing at j plus r squared. And that means that if we keep on doing this recursively, we can prove that we get the claim. Now the j plus 1 norm squared is less than or equal to the jth norm squared plus r squared. So it's less than or equal to the j minus first norm squared plus 2r squared, and so on. Are there questions about this? Okay. So what did we prove and why? We proved 2 things. That the norm of wj plus 1 was greater than j times gamma, and that the norm squared was less than or equal to j times r squared. What can we conclude? How can we finish? Suppose you were given these 2 inequalities. How could you possibly put them together? Yeah, we could just square the first one and put them together like that. If we square the first one, we get that j gamma squared is less than or equal to JR squared. I guess it's less than JR squared. And just moving things around, there's a J squared on this side, cancels with one of the J's, one of the J's cancels with this J, and we get this. So that means that we know that J is less than or equal to R over gamma squared, which is a constant. That means that we cannot have more than this number of iterations because we have a lower bound and an upper bound that will cross at that point. So we have basically a lower bound and an upper bound that are both growing with J, but they are getting closer together. And once J gets bigger than this, they will cross. So J cannot get bigger than this. But there's only one way that the algorithm ends. Whoops. There's only one way that the algorithm ends, and that is if we couldn't find one of these points, xk, that was misclassified. So as long as we can find a point that's misclassified, we can take another step, and these two inequalities will have to be satisfied. As a question, how did we figure out this? It's just literally by taking this thing, squaring both sides, and combining it with this thing. We know that this squared is less than or equal to this, and this squared is greater than or equal to this squared. So that means this is less than this is less than this. This is an example of a proof which looks like magic, but where you can sort of follow each step, hopefully. And I encourage you to go back at the look at the slides if you were confusing some of the steps. This is not a proof that I would expect you to be able to come up with. It's not a proof that I would expect me to be able to come up with either. But it is a relatively short proof that shows that this algorithm has to converge. You can also think of this as very similar to a monovariance proof, where we showed that, remember, monovariance proofs are showing that something is getting smaller and it can't go past 0. So we can look at the gap between the upper and lower bounds, and we can say it's getting smaller and smaller, and it can't go past 0. So this is basically a version of a monovariance proof to show that this thing terminates. Again, I wouldn't expect one to come up with this perceptron learning rule. It is slightly magic, and I can provide a little bit of intuition now, and maybe provide a bit more intuition later. The basic intuition is that by adding this point xk, we are moving the boundary to make it easier to classify that point correctly. It's like pushing the weight vector in the correct direction. And that's a sort of geometric thing, but if you sketch it out, you can see that basically moving this weight vector like this is basically saying it's pushing it towards the correct direction. And with enough of these pushes, you are going to improve your classification each time. And you can't improve your classification by more than a certain amount, because past a certain amount, you have got a correct classification. So this is why it's a monovariance proof. This algorithm only works if the data is exactly linearly separable. It will completely fail if the data does not have this correct hyperplane separating the positive from the negative examples. And the reason why it completely fails is because all of this proof relied upon the fact that there was a W star here, where things were either on one side of the W star or on the other side. So this is the perceptron learning rule does actually not work under noise, or at least provably it does. The proof doesn't work under noise if you have noisy data points that are just mislabeled on one side or the other. Okay, we will continue with neural networks next week. Again, the classes next week are Monday, Wednesday, and Thursday. Have a good weekend, everyone. As usual, please feel free to ask questions about the problem set in the Slack.